My name is Rajiv Mistry, and I'm accompanied by Jonathan Ortega and John Kai in presenting the topic title Quantum Frequency Detector for Bach's Cello Suite Prelude. This is a final project submission for applied quantum computing algorithms and software taught by Professor Pramay Upadhyay at Purdue University Department of Electrical and Computer Engineering.
So our group have selected to present the quantum Fourier transformation, finding the frequency in an audio file using the quantum algorithm. More specifically, an audio file goes in as an input and the most dominant frequency will be outputted. Before going in more detail about the quantum Fourier transform, I would like to point out the better off of using QFT over classical Fourier transform. Two aspects, the data representation and the speed. Classically, a dimension n vector would need n floating point numbers. On the other hand, in the quantum computer, the QFT operator on the wave function needing only the number of qubits log of n with the base of 2. This saves a lot of space. In terms of the speed, when we compare the big O function between the classical Fourier transform and the quantum Fourier transform, for classical, it is O n log n, while QFT runs in a time of O log n squared. This is also a large execution time difference. This can lead to our first point in the slide when we are detecting the frequency in the audio file. Using QFT is better off over classical Fourier transform, especially detecting the given frequency within rapidly changing frequency audio file. Now going back to our project overview or strategy, our project demonstrates the QFT algorithm with the input audio file and the quantum circuit, providing the outputs of qubit state, probability histogram, and the frequency distribution plot. We found an article of quantum computing to find frequency in an audio file. In the article, QFT algorithm was using the input of 9 Hz waveform. Later, we changed the input to our own waveform, which is the classical guitar sample. By using the tool of IBM Quantum Lab and local Jupyter testing environment setup, we have validated code from the article being run in our end. 900 Hz input using the QFT algorithm gets the 5 top frequencies. The fundamental concept that was introduced in the circuit was changing of basis from the computational basis to the Fourier basis. In other words, by using the hard mod gate, the qubit changed states from 0 or 1 state to plus or minus state. Also, using the control phase gate, desired superposition was achieved among the qubits. When we talk about the process more rigorously, first we introduced the waveform into the quantum world, which was representing the data. This was done using the PyDot package in Python, which is a library that can handle read and write wave files. After that, the state preparation, the Qiskit provides us with the inbuilt function for preparing arbitrary quantum states. Within this black box with the given input frequency, generalized Schmidt coefficient, CNOT operation, unitary operation, and basically changing the computation basis state into Schmidt basis state was performed. After the quantum circuit is run at the end, each qubit was measured in the polyZ basis. In other words, all the qubits collapse into one of the 2 eigenstates of the polyZ operator. Qubit collapse in a way that gives us the Fourier transform of the input amplitudes. 4 trials ran, and during each trial, we increase the number of qubits and see how different results are being obtained. Lastly, we ran the same QFT in a real device online by changing the backend from QASM backend to real backend and explore the results. On the very last step, we then change the input to the guitar song and repeat the steps, doing the 4 trials, each for QASM backend and real backend.
What is shown here is a composite view of 3 snapshots of the entire quantum Fourier transform circuit for a 6-qubit model. As you can see, the first qubit, as shown on the bottom line here, has a Hadamard gate that introduces superposition, followed by successive pi pulses that essentially change the state of the system. And then the next qubit receives its Hadamard gate, and then n-1 pulses are applied, and so on until we arrive at the final pulse that is given to the last qubit in the circuit. We've used this model to essentially allow the calculation to occur at 4 different trials for 4, 6, 8, and 12 qubits. One of the things that we did at the very end is to also apply swap gates. And this is, again, one of the techniques applied in quantum Fourier transforms. As indicated earlier, we did 4 trials with 12, 8, 6, and 4 qubits. We used 2 input files, 900 Hz and the Bach Prelude song recording. Both files were at 44.1 kilohertz sampling rate, and frequency resolution was 24 bits. All 4 simulated trials were successful. The pi pulses for the phase gates were applied based on n-1 steps. So if it was 12 qubits, we used 11 steps, and so on. The results of the pulses are shown in the screen captures for each of the trial runs based on Bloch sphere states. The final state achieved in all 4 trials was -x, which indicated success. For the real device trials, the 900 Hz trials had failures except for 4 qubits. And for the Bach Prelude file, the real device trials were successful except for 12 qubits. I will be discussing those results next. Let's take a look at the simulated trial results for these 4 runs for each of the 2 input files. I will go through these quickly so that you're able to see the histogram plots indicating the top frequencies found, as well as the frequency value plots against differing sample counts for each of the runs. We start with 4 qubits, and the accuracy was not as high as expected for 900 Hz. And then we moved to 6 qubits. The waveform started to get accurately depicted, as did the sharp peak shown in the orange curve in the value plot. The histogram also showed fairly good top 5 frequency detail. For 8 qubits, it was also good results. We have a very good depiction of the actual sinusoidal waveform for 900 Hz, and the peak is also visible in the orange curve. The histogram plots also show peaks that are indicative of detected frequencies that were dominant. And the same for 12 qubits. The next set of runs is for the Bach Prelude recorded wave file. The 4 qubit results were not very accurate. Essentially, the waveform did not get captured because apparently the sample count was too low, or the qubit count was too low to be able to detect it. The top 5 frequencies were not very well detected, although there were some peaks in the histogram plot. Good results for the 6 qubit run. We can see 5 peaks in the orange plot that indicates the top 5 frequencies detected. For 8 qubits, we also saw a really good depiction of the actual waveform in the audio recorded file. And for 12 qubits, we saw really good results in terms of both the peak detection in the histoplot as well as the actual waveform captured in the value plot. The next set of results discusses real device trials. For 900 hertz, the 4-qubit trial worked well. It captured the waveform of the input file accurately. However, the peak detection was not very good in the real device. We had a failure in 6 qubits, which was module object not subscriptable. We didn't know what to make of it, so we moved on to 8 qubits. With 8 and 12 qubits, we have the same error. Circuit runtime is greater than device repetition rate. Apparently, on the free account for IBM Quantum, we did not have the ability to reserve sufficient time to allow the job to complete. And then for the Bach prelude file, we had not so good results with the 4-qubit run. It did offer peak detection, but the waveform of the actual input file was not very accurately calculated. For 6 qubits, we started seeing good depiction of the waveform as well as really good peak detection as shown in the value plot and the histoplots. For 8 qubits, very good waveform detection of the input file, not very good frequency peaks detection as shown in the orange curve in the value plot. The histogram does show some peaks, although the results are not certain that they were accurate. With 12 qubits, it failed with circuit runtime being greater than the device repetition rate.
So once we were able to install all the dependencies that our project required and run the code without any errors, there were two main things that really helped streamline our process. The first was to combine all of the Python modules that the author put out into a single Jupyter notebook. So we went from about 6 or 7 files of Python modules to just a single notebook. And that really helped remove a lot of the clutter. So I think we removed about 50 lines of just imports because we could put it all into a single cell at the top of the notebook. So there's that. And then secondly, on the right here, you'll see the function that we made called top 5 detected frequencies. And so this just took 3 parameters based on the trial, and then we printed out the frequencies that we found, got the counts, assembled the circuit, drew the circuit, and then output the final state qubits, and then returned counts with a filter. So you can see here on the left we have counts being redefined after running the function, and then counts being redefined again based on this parameter y being greater than 100, and we just chose a value for each trial that made the histograms look nice because the near zero probability qubits really cluttered up the plots. And then I'm going to go ahead and talk about some real world applications. Firstly, unsurprisingly, I'm going to talk about cryptography. We're all pretty familiar with Shor's algorithm by now, so I'm not going to waste too much of your time. Just a reminder that QFTs provide a bulk of the speed up that Shor's algorithm has over classical prime factorization algorithms. Secondly is image processing, and so an important operation in image processing is convolution, and you can basically think about convolution as like when you're applying a filter to an image. So if you have like a regular image and then you blur it or enhance it or apply like anti-aliasing, those would be examples of convolution. And so when you Fourier transform an image, you can apply convolution, and the operation itself is multiplicative in the frequency domain, and so that means it's a lot less taxing and easier to do. And then on top of that, since you're using quantum Fourier transforms, you have reversible transformations, and so you could actually just have an image given to you and be able to get back the original image that some other person started with. And then on top of that, this is something that John touched on earlier, but it's important to remember that with some of these applications, they're not necessarily always faster or not even as fast as classical methods. But even if they're not, they can still provide other advantages like the reversible transformations and also data storage. So in the second line here, if you think about a 16 megapixel image, that can be encoded in just 12 qubits, and I mean, that doesn't sound that impressive maybe to you, but if you think about like a video, which has a lot of 16 megapixel images, the benefits become a lot more apparent. And then thirdly, I'm going to talk about differential equation analysis. So in looking through this paper here, the second reference on the bottom, this group of researchers talk about some of the problems they have with quantum linear equation solvers and quantum machine learning algorithms. And so one of the big ones with solvers is that you receive quantum states as output, and for machine learning algorithms, you receive they require quantum states as inputs. And so what they did is, well, specific examples, of course, they were able to combine the two and make it so that the output for quantum linear equation solvers would be the input for quantum machine learning algorithms. And so when they did that, they were able to have exponential advantage over classical Monte Carlo methods. And so these are just some of the benefits and applications of QFTs. And that's the end of our presentation, so thank you.